Hello. This is Concrete Path. This lecture is designed for solving the problems of Mohrs circle and stress transformation. Let's go and get the stresses. So number one, that you have a state of stress on a particular element. So this is your element, and you got a stress of sigma x equals to 50 MPa, 50 megapascal, and you got a 40 megapascal shear stress tau. Similarly, we can show here also. So but the here is, yeah, we got also sigma y equals to -10, or we can say compressive stress of compressive stress 10 megapascal. So we can say sigma x is 50 megapascal, sigma y is -10 megapascal, and your tau xy is positive 40 megapascal. So we need to get the principal plane. We need to get the principal stresses sigma 1 and sigma 2, and we need to get tau max also, shear stress, maximum shear stress, and we need to get the locations of those planes also, theta p1, theta p2, theta s1, theta s2. So actually there are, if we have a particular beam, then we say from the SFD and BMD we get some maximum shear stresses and shear force and maximum bending moment, some sort of bending moment. So then we say let's take any particular point. We want to say if the shear forces we say the shear stress would be V by cross sectional area. If you divide that by cross sectional area, then we can get shear stress. Similarly, if you have bending here, you got bending moment at any particular point. So we say the bending moment that is related to your bending stress by formula, that's flexural formula. So this gives your stresses. So similarly, you have got those stresses on a particular element. So you are now supposed to calculate the transformation of stresses, that how these stresses would be having the particular value on those planes where they are maximum. Want to say if they are transformed, how much are they transformed? So we want to get those principal planes and these. So if you plot them on a Mohrs circle, we say this is Mohrs circle. Every point on the Mohrs circle represents state of stress. So this is, if I say this is plane number one, this is plane number one. So this is plane number one. I can say this is plane number one, and next plane is some sort of, next plane is this plane. I can call it P and Q. So Q plane is some other plane, Q plane, but they are located such that in the stress element they are located at 90 degree from each other. But we know in the Mohrs circle we have to represent them at location of that 2 theta, that we say if the angle between the two planes is 90 degree here in stress element, so we have to align them at 180 degree from each other. So if this is P, so the angle between them should be 180 degrees. So that 2 theta came from the derivation we have, that derivation when we derived that sigma x dash minus c whole square plus tau xy minus 0 whole square plus equals to some root, and we said that this is r square. So yeah, r square is some sort of root, that the formula for that we know. So in that there was some relation initially, that it was in terms of sine 2 theta and cos 2 theta. Then we say, when we square the terms, so it became sine square theta plus cos square theta, sine square 2 theta plus cos square 2 theta, that is equals to 1, but the theta was in terms of 2 theta. So that's why here in this Mohrs circle the equation came, but the theta was in actually 2 theta during the derivation. So let's solve the problem now. So this is your state of stress given. We need to get the maximum principal stresses and their locations, and tau max plane and their location. So we have the equation for principal stress location. We know that tan 2 theta p equals to 2 tau xy by sigma x minus sigma y. If we use that value, that equation, if we say that 2 tau is your positive 40, sigma x is your 50 minus of sigma y is minus 10. So we write this value you got, then you calculate it, you get a value of theta p equals to 26.56 degrees. So if you got theta p1 at 26.56 degrees, so let's calculate the value of now sigma 1 or sigma 2. We know that sigma 1 or sigma 2, that equals to sigma x plus sigma y by 2 plus minus root of sigma x minus sigma y by 2 whole square plus tau xy whole square. So substitute the values here. So we have sigma x equals to 50 plus minus 10 by 2 plus minus, then you have root of that sigma x minus sigma y by 2. So we can write sigma x minus of minus sigma y by 2 whole square plus tau xy. Tau is your value of 40 square. So we got a value that sigma 1 equals to that we can say 20 plus minus 50. So we can say 1 is your value of 70 megapascal. Next one is your value of minus 30 megapascal. So to verify it on which particular plane your sigma 1 is acting, so we can also derive that. So if we substitute value, if we substitute the value we got at that theta p, if we substitute that value of theta p 26.56 degrees, if we substitute at theta p equals to 26.56 degrees, your stress value, we can write the equation sigma x dash equals to sigma x minus sigma y by 2, sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 cos 2 theta plus tau xy sin 2 theta. If you substitute here those values which you are given in the stress element, that you are provided with in the stress element, so we can substitute those values, that sigma x was equals to 50 plus then we have plus, then sigma y was minus 10 divided by 2 plus, then similarly you can write 50 minus of minus 10 divided by 2, then cos 2 theta, cos we can write 2 theta plane, principal plane, this one, and plus tau xy. Tau is your 40 and sin 2 theta p. So you get a value of that sigma x dash equals to plus 70 megapascal. So once you got the plus 70 megapascal, that means you show the sign by a different color, that sigma positive means, if you got a positive value, that means the arrow should be in this direction. During the derivation we show the arrow sigma x dash in the direction. So if your element was like this, so you have to draw a plane at theta p equals to 26.56 degrees. So your theta p is 26.56 degrees at that angle, at that plane. So at that angle from with respect to the vertical in anti-clockwise direction, you have to draw a line that shows that particular plane. So let's draw that particular plane. So at an angle of 26.56. So we say that this is our desired plane. So we can say this theta p equals to 26.56 degrees. This is our, so if you show that the stress element here, the stresses on this particular element can be shown here. So on this particular element we got that, see, we got theta p equals to 26.56. That means on this plane normal stress would be acting, and we got the direction also, that the direction was as per the direction of during that we have during the derivation also. So we can write here sigma 1 is that 70 megapascal. So if this is 70, we can now say that this is also 70, then this should be minus 30, minus 30. So sigma minus 30 is your sigma 2. So we got these values, we got these values. And if you want to say what's the value of tau max, we know that tau max value equals to that value of this root r, that this is tau max. So your tau max is equals to 50. So tau max equals to 50, you can write tau max equals to 50. And this is positive. That means direction should be in this direction, in this way. And what should be the location of theta shear? That in this that tau max plane should be located at an angle of theta p plus 45 degrees. Is it? Can we say that theta s equals to theta p plus 45 degrees? So your theta p is 26.56. You can write we can get the value like some sort of 71.56 degrees. So we got the 71.56 degrees. You draw a line at an angle of 71.56 degrees. So this is our, we can say this is a particular line at an angle of 71.56 degrees. Or we can say from this element also it should be in this direction also. We can say this should be the direction actually. So this direction should be there. So this should be our angle that. So this is our theta s, theta shear. With respect to the vertical, you have an anti-clockwise theta s equals to 71.56. So on this element, you have to represent the state of stress. So let's say that we got the tau max equals to 50. So we can say tau max direction should be this one. So we got tau max equals to 50. Then finally we can say other values also. We can say this is 50, this is 50, and this is 50. And once we got the tau max, there can be associated normal stress also. So we can say tau at the rate of sigma at the rate of tau max. That the equation for that equals to sigma x plus sigma y by 2. Sigma x plus sigma y by 2. Sigma x was your value of 50 plus sigma y was minus 10. So you got a value of 20, and that's also positive. So positive in both the planes. You have 20, 20, 20, and 20. So this is your tau max plane. We can write this is your tau max plane. So we got this problem now. So if you want to say if you want to draw it using the Mohrs cycle, let's say we draw a Mohrs using the Mohrs cycle. Let's say this is a Mohrs cycle. So, and we say this is our reference line. Let's take a different color. So this is our reference line. We can say this is our sigma x line, and we don't know where it will cut the origin. Either will it cut the origin or not, that we can check here. So initially, what was given that? So this was given. I can remove the rest parts. So actually, so it was given that you got a plane P. This was your plane P, and this was plane Q. So you are having two planes. One is having a normal stress of minus 10. So if you say plane Q is having, so this is our plane Q. It's having a normal stress of minus 10, and a shear stress. We can say shear stress was in this direction. Shear stress. So this was our shear stress. That means if it tries to rotate the element in the plane, if it tries to rotate the plane in clockwise direction, we say shear stress is positive. So if you want to plot it, let's say let's say we want to plot it. So this is our so we can represent the coordinates. I would say minus 10 comma your shear stress value was 40, so minus 10 comma 40. So if you want to say this is sigma x, and in the vertical we say sigma that tau xy, so you need to represent minus 10 and plus 40. So if the sigma is minus 10, that means it will cut the origin also. So let's say this is minus 40 somewhere here. Let's say somewhere here minus 40 comma, yeah, minus 10 comma 40, minus 10 comma 40. So that means the line, the origin line should be here somewhere here. So we know that two perpendicular planes are represented at an angle of 180 in the Mohrs circle. So next plane is that you got plane, this is, we can say this is plane Q, and your plane P is looks like this one. So this is our plane P. Here the sigma is acting positive 50, and a shear stress that's acting in the anti-clockwise manner. So it tries to rotate the element in the anti-clockwise manner. So we can say your minus, so your sigma is positive 50. Let's say sigma is positive 50 here somewhere, and positive and negative tau value of 40. So let's say this is one more point. So these should be at an angle of 180 from each other. So let's say they are placed here. So we got a value that this point, this is the central point. We know that the center value equals to sigma x plus sigma y by 2 comma 0. And if you substitute the values 50 plus minus 10, and you can get the values that that's 20 comma 0 sigma x plus sigma y, yeah, 20 comma 0 that you earlier got, yeah, 20, 50 plus minus 10 divided by 2, 40, 20, yeah, you got a center value of 20. So from the origin you are having a center value that's at 20. So if you want to find that what should be that value, you can now, if you draw the Mohrs circle, so actually the Mohrs circle is drawn in this fashion, that once you have center, once you know center equals to sigma x plus sigma y by 2 comma 0. Next one, you once you got the center, so you can say now what's the radius. So after that you have to say what's the radius. Radius equals to, you know that radius formula, sigma x minus sigma y by 2 whole square plus tau xy whole square. So once you got the radius also, you can now draw a circle. Then after that you would represent two planes, P and Q plane. So after that you represent plane P and Q. Then after that you can get the location of those principal planes and tau max planes. Since if you in the exams these protectors are not allowed, that means you have to go through the formula that we have tan to 2 theta p equals to 2 tau xy by sigma x minus sigma y to get the location of principal plane. Otherwise you can say this is my plane, this is my plane P, and I can now calculate this angle. What's the angle? If I know this angle, I can say this is 2 theta angle, because here the sigma is, because here on this plane here the sigma is acting, that's called as principal stress, and that's also major principal stress. And here this is plane B, here the sigma is sigma 2 comma 0, and this is also principal stress. And we got the values that this was equals to minus 30 comma 0, and this was equals to 70 comma 0. So then you can say what's the value of this point if you know that through the protector. But if you are using through the calculation these directly, if you are directly using those equations, then you can say sigma 1 is equals to C plus R, and sigma 2 equals to C minus R, where C is center and R is your radius, and you can calculate that C was 20 and radius was 50, so you can get 20 plus 50 and 20 minus 50. So we can say this angle should be equals to this angle should be equals to this angle can be calculated also, that's equals to tan 2 theta p from that, and you have to go twice that angle. So once you got the angle of 26.56, actually the angle was 26.56, so you can say now the angle 2 theta p should be equals to 26.56 into 2. So you have to go at an angle of some 52, 53 some angle. After that, what's the location of theta where the shear stress is maximum? What is the location of tau max plane? So that's at angle of, we can say 2 theta s, or is at an angle of 90 plus theta 2 theta p, we can say this one. So once you got some value of say 53 degrees, let's assume, then you have to go 143 degrees. So we have to go 143 degrees such that the angle here is 90 degrees, because actually in the stress element, tau max plane and principal plane are at angle of at an angle of 45 degrees. In the Mohrs circle, they are at an angle of 90 degrees. So this was our first problem. Let's calculate now next one. So actually I want to show something, that this is, let's say you got some value of principal plane 1. So you can say this is principal plane 1, because on that plane some sigma is acting, that's sigma max, we can say sigma is acting, that's called as sigma max or sigma 1. Then we have perpendicular to this plane, there is one more plane which we call as second principal plane or minor principal plane, because on this plane there is some sigma 2 acting. Then after that we say there are shear stress planes also where shear stress is maximum, that we call as tau max planes. They are at an angle of 45 from either of those planes of principal planes. So let's say any plane, you take any plane, let's say this is our line, such that it will make 45 degrees. So we can say this is 45 degrees, and we can say this is tau max plane 1, and similarly we can have two tau max planes. There are two chances of making those tau max planes are 2. So finally you got two maximum tau maxes and two maximum normal stresses. So then you represent them on a Mohrs circle. Then you say this plane, this is plane 1, principal plane 1, this is principal plane 2, this is tau max plane 1, and this is tau max plane 2. So out of those infinite number of planes, we are worried about these 4 principal planes. Yeah, these planes, not principal planes. We are about these worried about these 4 planes. Let's take one more problem. So let's say you got a stress element. With a compressive 200 megapascal here, and anti-clockwise, and we can say negative shear stress 200, and a tensile sigma y 400. Similarly, you can show in this direction also that this is this. So we got this. You need to get the value of principal plane location and their stresses also, and also tau max plane and sigma associated with the tau max plane. So if you use the equations, we can say your sigma x is positive, sigma x is minus 200, sigma y is plus 400, and tau xy that equals to minus 200. Now you know the equations. Then you can say from tan to theta p equals to 2 tau xy by sigma x minus sigma y. Then you can get the value of theta p. If one theta p is there, then you can say next to theta p is at an angle of 90 plus first to theta p. Then let's say you got the values of and let's say the location is 16.84 degrees and 106.84, because this one should be 90 plus theta p1. So we got the two principal planes. Now we want to say what are the values of maximum normal stresses, or we can say principal planes, sigma 1 comma 2. That's, we know the equation, sigma x plus sigma y by 2. So we can write sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 cos 2 theta p. This we can write represent this one. Yeah, actually we have the direct result that this one, this is for check, and we can directly use that one, sigma 1 comma 2, that equals to sigma x plus sigma y by 2 plus root of sigma x minus sigma y by 2 whole square plus tau xy. Tau is also minus 200 whole square. Then we can say use sigma 1 comma 2, that we got as 100 plus minus 360.555, and we can say this is our, that the tau max, that the sigma 1 that equals to 460.555, and sigma 2 equals to minus 260.555. That means one is tensile stress, next one is compressive stress, that is maximum principal planes, that means maximum principal stresses. So if you want to say what's the tau max, this should be the tau max. And tau max is also calculated. If you got those sigma 1 and sigma 2, you can say tau max equals to sigma 1 minus sigma 2 divided by sigma 1 minus sigma 2. That you can also do. Now we want to verify that what's the at what theta p, because we got two theta p. One is your 106.84, next one is your 16.84. We want to say at what theta p your sigma 1 is acting and sigma 2 is acting. So let's use that equation. We can say this is sigma x dash, then we can write that equation, sigma x dash, and the values, and we know the equation that sigma x dash equals to sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 cos 2 theta p. Let's take this value at the rate of theta p equals to 16.84. You substitute the value of here, that 16.84, then you calculate it, tau xy sine 2 theta p, and you get a value that sigma x dash equals to minus 260. So minus 260.55. That means this is the stress that is sigma 2. It's not sigma 1. So we got a sigma 2 compressive stress, that is minor principal stress acting at theta p1, we can say. Actually we calculated this one, it was theta p1, but it's now theta p2, because we had to now see from the check, we can say that at theta p equals to 16.84, your normal stress value came out to be minus 260.55. That's also sigma 2. So now if you want to show on the stress element, so let's say this was our stress element given in this fashion, some sort of loading stresses were there given there. So then with respect to those, and we had to go 16.84 degrees. So 16.84 degrees. At 16.84 degrees, your principal plane is there, on which this is principal plane 2. We can say this is principal plane 2, because on this plane your sigma 2 is acting. But sigma 2, is it positive or negative? We got a minus 260, and show the sign that it is negative. That means in this direction. Show the direction that it should be in this direction. Minus 260. So we can remove this one. So this is minus 260. So minus 260. Minus 260.555. So if this is minus 260, this one is also minus 260.55. And next plane is this plane, that on this plane your maximum normal stress is acting, that we call as major principal stress, that is sigma 1, that was equals to 460.55. So this was your sigma 2. So we have shown the stress element also, those principal planes also. And if you want to calculate now location of theta shear plane, we know that for this also we have equation that inverse of the what we have for the tan to theta p. Actually the relation here is tan to theta p into tan to theta s equals to -1. -1. Yeah, -1. So this is one relation that that tan to theta p into tan to theta is equals to -1, because in this one we have 2 times 2 tau xy by sigma x minus sigma y, and in this one we have minus times sigma x minus sigma y by 2 into tau xy. So if you want to say what's the location of theta that tau max plane, we say if you got theta p, then you add 45, or if you subtract also you can get location of that maximum plane. So if you say let's add, because we are going that will make our calculation easy, because we are going anti-clockwise, so we can add that. So that was your theta p was equals to, let's take that value 16.84, and you add that 16.84 plus 15 degrees 45 degrees, you got value of, let's say 61 point something, 61.84, and you show that element also. So if you go from here, actually this was your first plane, that principal plane, at an angle of 16.84, but if you go to an angle of that's equals to 61.84, that's your shear stress plane, that should be cutting this element at 45 degrees. You can say this one, this way should be that element. So if you want to show that element now, tau max plane, we got a tau max value of, that was root of that value, that was positive. Tau max was positive. Tau max was positive. Yeah. So if tau max was positive, that means you have to show in this direction. The value was some 360.55, some 360.555. So others should be also 360.555. And we want to say what's the normal stress at this tau max plane, that sigma equals to sigma x plus sigma y by 2. So sigma x was minus 200 plus sigma y was positive 400 divided by 2, that's 100. So we can show also that one, 100, 100, and 100. So we got this one. So if you want to represent by Mohrs circle also this problem, so let's make Mohrs circle. So this is Mohrs circle. Let's calculate those values directly. So this is our sigma x line, and there is sigma y line. We don't know where is the origin. Sigma y line. Then we have initially given was that the given data was this is 200, and let's call this plane name as P plane, and this was Q plane. So on this plane, tensile 400 was acting, and shear stress was in this plane here in this fashion. So the direction should be in this way. So if you have one plane that's Q plane is somewhat in this fashion, and you are applying a sigma, positive sigma, and you are applying anti-clockwise tau here, anti-clockwise tau. So we can say plus 400 minus tau value was 200. So minus 400 comma plus 400 comma minus 200. So plus 400, let's say plus 400 is somewhere here. Let's say this is plus 400 comma minus 200. We don't know this line where the origin is, but once we know the center and radius, we can draw the circle. Then we can say from the origin, if there was some origin, so this was origin, we can say what's the from the origin, what's the value of center. So we can, with that we know sigma x plus sigma y by 2 center. Once we got the center, then you say what's the radius value. So if you got 50 radius, then you take a, you draw a circle 50. So if you're doing that directly, you don't know directly how, but one thing is that you can say it should be somewhere here, that plane Q, it should be somewhere here, plane Q, and plane P is somewhat in this fashion. You are applying a negative sigma, that minus 200, and shear stress is in this direction. So we can say shear stress is, it is clockwise, so we can say positive shear stress, positive 200, minus 200, and minus 200, and plus 200. That means sigma x is along the negative axis, and tau xy is above the sigma x line. So that means origin should be somewhere here. Origin should be here. So we call this plane as plane P. So this is origin, and you join the two lines, two planes, we can say. These are your two planes at an angle of 200, that at an angle of 180. So this value is equals to C, center. This is center. So this is our 2 theta P, but we don't know. See here, this one, we can write this one as tan 2 theta P1, because your sigma 1 is acting here, sigma 1 comma 0, and sigma 2 comma 0 is acting here. So we got two values of sigma, that one was equals to 460, yeah, 460.55. Next one was minus 260.55. So if this is 400, then this one is 60.55. So then we can go up to an angle of 2 theta P plus 90 degrees, such that we can get tau max plane. So this is tau max plane. This value is tau max plane. Tau max, we can say tau max is there. And similarly, we can also show here, this is tau max. So we got this one also. If you want to show in detail, so let's make it in detail. So let's say this is our first principal plane at an angle of 2 theta P, that we calculated that first, but it's showing that it is with respect to the plane Q. Your 2 theta P is with respect to the plane Q. Yeah, that means, see, we got a value of theta P. We got two values of theta P. Wait a minute. We got two values of theta P. One is 16.84. Next one is 106.84. So that means what should be the value of 2 theta P? That means some 34 and some value of 212. That means you have to go 34 degrees and 212 degrees on Mohrs circle. But both are with respect to the plane P. This is important here. Both are with respect to plane P, and that is also in the anti-clockwise direction. So once you plotted the plane P and plane Q, you have to show the angle also with respect to that plane. So this is, I can say, I can show it now in a proper way. With respect to the plane Q, your tau max, your sigma 1 is acting at an angle of 2 theta P, that was equals to some value of 2 into 106.84, that equals to some value of 106. Let's say that equals to 213 degrees somewhere. So we can say from the plane P, so this is plane P, from this plane you have to go at an angle of this one. So this is our, you can say this angle, that is 2 theta P1, that equals to 213 degrees. So this part is 180, and this part is extra, that 213 minus 180. So this is our principal plane 1 location. You can say this is our principal plane 1. This is principal plane 2. Now once you got the value of theta p1, now where should it be the value of the theta p2? So you have to go at an angle of 2 times 16.84. This is our 33 something, 34 degrees. So this is, you can say 2 theta p2. Now both are from plane P. Similarly, if you want to say where is the tau max plane, so you have to go at an angle of, we got the value of theta s was equals to 61.84. That means 2 theta s equals to 122, 123 something, 123 degrees almost. You have to go up to an angle of 123. So 123. So somewhere here, you have to reach somewhere here. So you can say here there is some tau max. It is not necessary it will go from the center. So somewhere here, tau max value. So here the angle should be between the two, 90 degrees. Yeah. Similarly, if you want to say one more plane is there, so you have to go minus 45 from. So you can either go from 45, you can go from theta p plus 45, or you can go theta p minus 45. Similarly, you can go to theta p minus plus minus 90. So if this was your principal plane one, you can go negative 90. The negative 90 means somewhere here you can have some value. If you draw the circle exactly from using those tools, you can get what the exact location of tau max is there. It's not necessary I plotted the circle on the line itself, so it looks like it's on the origin. Tau max is on the origin, but it can be somewhat in this fashion. It can be this way. It can be negative way also. So there are n number of possibilities. So let's go for one more problem. So we have a steel plate. It's given that we have a steel flat plate in plane stress condition. That means only sigma x, sigma y, and tau xy is acting in plane stress condition. So we have sigma x equals to 10, sigma y equals to 6, tau xy equals to 8. Both are, each of the unit values are in kilonewton per mm square. So let's have that stress element. So sigma x is positive 10, tau xy is also positive 10, positive 8, and sigma y is 6. So we need to get value of sigma 1, sigma 2, and their orientation location. So directly we can say sigma 1 or 2 equals to sigma x plus sigma y by 2 plus minus root of sigma x minus sigma y by 2 whole square plus tau xy whole square. So we get the value of sigma 1 comma 2. So that equals to 8 plus minus 8.2461. This part is also tau max, and we can say this is 16.246, and we have one more value of, so we can say this one is sigma 1, and sigma 2, we can write that sigma 2 equals to minus 2.46, and we know the formula for a location of the principal plane. We know tan 2 theta p equals to 2 times tau xy by sigma x plus sigma x minus sigma y, and you get a value of theta p equals to 37.98. And if you want to verify it, cross check it, you can say at the rate of theta p, you use the equation sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 cos 2 theta plus tau xy sin 2 theta p. Use the value of theta here equals to theta p, and you can get the value of sigma x. That comes out to be equals to sigma x equals to 16.246. That's also your maximum principal stress, or we can say major principal stress. So let's let's have that stress element at an angle of 16.246. So 16.246. So at an angle of 16.246. 16.246, you show the element that on this plane, your sigma 1 is acting, that's maximum. That's maximum. That's maximum value of that we got 16.246. That means next one should be compressive, that we got minus 2 point something. Minus 2.46. Minus 2.46. So this is sigma 1. Let's make the Mohr circle. Say this is some sort of circle. This is some sort of circle. Your So on the plane P, we have stress that sigma x is positive 10 and minus 8. We have tau xy. So similarly, we have plane Q on which sigma 6 is acting and tau xy is in this clockwise direction, so positive. So your 2 theta p equals to 37.98 into 2. So you got 75.96. So this is your angle 2 theta p. We can end this class now. Time is over. See you again